10.2, Example 5. In this example, we're finally going to look at how to find velocities and acceleration when given vectors. So we have a particle that moves in the plane so that its position at any time is given by sine of t, 1/2 of t squared. So the first thing we're going to want to do in this problem is find the position vector of the particle at any time t. And this couldn't be simpler. Because we're given the position, all we have to do is turn that point into a vector. And that's it. For part B, we want to find the velocity vector. Well, this is super easy. All you do is do the derivative of each portion with respect to time. So the derivative of sine is cosine, and the derivative of 1/2 t squared is just t. The next thing I want to do is find acceleration. Again, super simple. Just do the derivative again. We get negative sine of t, comma 1. And this is our acceleration vector. So for part D, it says describe the position and motion of the particle when t equals 6. Well, we typically denote position as x of t, and that's going to be sine of t, comma 1/2 t squared. So then our position at time 6 is just going to be sine of 6, and that's just a number, and 18. And all I did was plug in 6 for t. So v of t is then going to be cosine of t, comma t. So then v of 6 is going to be cosine of 6, comma 6. And our acceleration was negative sine of t, comma 1. So then the acceleration at time 6 as a vector is negative sine of 6, comma 1. And that's it. So now what I want you to do is go ahead and copy down some definitions that has to do with vectors and their derivatives. So the particle's position is we call r of t. For vectors, we call it r. And it's x of t, comma y of t. The velocity vector is the derivative of x with respect to t, derivative of y with respect to t. The particle's speed is denoted as the absolute value of v, or we call it the magnitude. The particle's acceleration vector is the second derivative of each one. And the direction vector is the original vector divided by the magnitude.